Adam here at TCT Show 2019 again, and this time I'm at the E3D booth with Sanjay. Sanjay, I think everyone probably knows who you are already who's going to be watching this, but in case they don't...
Yeah, I'm a big deal on a niche proportion of the internet.
Would you like to introduce yourself?
Yeah, I'm Sanjay. I'm one of the founders and directors of E3D. We make things that squirt plastic out of small holes.
Excellent. So today we've got this new Hermes product. What is it about it that you want to tell us? What makes it special and why do we need to buy it?
Yeah, I mean, Hermes is our best product ever by a clear shot. It's a compact, complete extrusion system with extremely high performance. So it's dual drive with extreme level of filament constraint. And what that means is that the drive gears feed the filament very directly into the heat break where the melting and processing of the plastic happens.
So great for flexible materials and probably other materials as well.
Yeah. And so obviously flexibles are the most obvious one because they're the springiest.
If there's a hole, they're going to go out of that hole.
Exactly. But even with the more rigid filaments, they're still behaving as a spring. Everything is a spring, just depends on the force, right? Just depends on the Hooke's constant. And so the shorter you can make it, the stiffer. Everything is a spring. It just depends on the Hooke's constant, right? And so the shorter you can make it, the stiffer that spring becomes. So the more responsive to flow, the more responsive flow is to the motion of filament and the motion of the gears. So even when you're just printing PLA, or even like the semi-soft-ish materials like nylon, you get those really powerful clean retracts. In fact, you can get really powerful clean retracts just on TPU as well, which is kind of mind-blowing. It's very cool.
So that heatsink looks a little bit different to heatsinks I've seen before. What's the element going on there?
Yeah, it's kind of inspired a bit by like computer GPU heatsinks. And so fans, they swirl the air and it has momentum, so it wants to kick out tangentially to the rotation of the fan. Yep. And so we place these fins at tangents to the flow, and that means that the air kind of flows more easily through the fins. It's already pre-directed into that way, as opposed to, say, aero, where the air has to go in and then immediately kind of laminarize and go out sideways.
So it was getting straightened in a way that reduced the airflow.
Exactly. So there's less resistance to flow, which means more air passes, which means more cooling happens. There's another neat trick here because we don't just have fins to push the air out to the sides. We have this wall here, this dam, and that prevents air being flicked downwards into the print envelope. And keeping that print envelope of very consistent temperature is very important, especially with high performance, high temperature materials that kind of need heated chambers and that kind of stuff.
So things like ASA and ABS, which would be sensitive to a bit of draft,
exactly.
You're immediately blocking that.
Yeah, and you'll probably see this on certain printers. You'll see that cracking happens on the exhaust side of the fan. So I don't know, if you have a machine with a V6 perhaps, the air's blowing through, and depending on how you have your exhaust air configured, one side of the print space is going to have a bit more kind of air turbulence and motion to it, which means a little bit of differential cooling, and that means warping and cracking. This gets rid of that. All the flow goes straight up. We did a lot of work with hot wire anemometers and figuring out where air is and isn't moving.
Sounds like a lot of proper engineering.
Yeah. Very unusual for us at E3D.
So the tensioning mechanism there also looks a little bit different to what I'm used to seeing. Can you tell us a little bit about that?
Yeah, so we looked at this from a kind of user-centric design process, both in terms of when we talk about users, our users are often printer manufacturers, as well as the end users who want to just mount it onto their machine. So we came to the realization that essentially you have to have access through the top to insert the filament. That's a given, but you don't always necessarily want access through the side because you may be occluding those depending on your design. So we made all the user interaction happen through the top. So instead, on almost every other extruder, the tensioning screw is like here, and then so you have to have access to that screw or a hole, and it takes up space. Instead, we flick the linear motion around 90 degrees with a pair of sliding cams. So when you tighten this screw up, the idler tension increases because that spring gets compressed, and you go the other way. And then if you want to you can load filament there, and you can engage and disengage with the kind of finger tabs. So it's just a nice bit of kind of ergonomics, and you just always know where to go, what to do.
That is one thing I noticed recently when I was putting a Titan Aero on one of my machines, that I had to find a way where I could access the tensioning screw, but also still find a decent way to mount it. And it was quite difficult. But yeah, with this, that clearly helps that situation.
Yeah, and with Titan Area, there's a gear sticking out the side that you also have to account for. On this, there's the T-slot mounts, and then you have a flat machined kind of surface that can bolt up against something. So very stiff orthogonal mounting is trivial.
Speaking of that stepper motor then, that doesn't look quite like a standard stepper motor. What's going on there? What's the differences?
All our previous extruders and pretty much every other extruder on the market, you take a motor and then you bolt your extrusion system to the front of it. But you end up making a casing or a body for your extruder system, and the NEMA 17's already got a casing or a body or a front faceplate put on it. So we may as well just conglomerate those two parts. So the front face of the NEMA 17 motor is the rear casing and bearing housing and supports for all the pins and stuff for the Hermes. So there's no wasted parts. Part count comes down, cost comes down, and it becomes a more compact, denser product.
Excellent. That sounds very good. So how does that affect, for a user point of view, obviously that's a specific mounting. How easy is that to mount? What are the mounting methods that they can use to do that?
You just pop little M3 square nuts in there, and then you can screw into them. So
easy as that. Sounds good.
No drama with sandwiching and mounting and putting it around things, which is kind of important because we want to be able to fully assemble, test, and qualify these extruders before they go out the door, so the user doesn't have to disassemble or put them together. And again, saying users, printer manufacturers, and just the guy who's building their own printer out there or modifying it, it just makes it a great deal easier to design mounts for and to mount. This clamshell just pops open, and then there's the filament drive system inside. And the heat break is so closely tolerant to the gears that we actually have to back it out a half turn before the gears are released, because they are so closely tolerant with the heat break that they actually interlock. Right. You see the filament path in there, and when I screw the heat break back up, you can actually see the heat break arrive at the filament drive gears. Do you see that? It's very hard to see.
Just a little bit. Yeah.
But it just pops out over the top and gets in between those drive gears. There's nowhere for filament drives. And you can see how short the filament path is, right? So the filament path just goes from, this is where it gets gripped and driven, and by here it's molten plastic, so that spring length is very short.
This does look quite unique. How is it going to interact with the rest of your product line that you already have?
So the heat break is new, and as we've gotten better at machining, we've been able to make finer and finer parts. So this heat break is an M4 heat break. The reason we chose that is the slimness allows us to get it right up to the filament drive wheels. And so the filament goes from the drive wheels directly into the heat break with no transitions, gaps or anything. So that slim M4 brake really helps with that. It also decreases the thermal resistance. So the ability for heat to get out of the heat break or out of the middle of the heat break or the bottom of the heat break into the heat sink, and there will be dissipated by the air, is reduced because there's less material for it to have to conduct through.
And then heat block and nozzle, same as before?
Yeah, heat block and nozzle the same as before. So you can use all your existing nozzles, Volcano, etc. They all just go on there. It's just that from the heat break down, it's all normal E3D stuff, as you know.
So this is a pre-production unit, right? When can the general user expect to be able to get their hands on one of these?
Yeah, I reckon in around 4 to 6 weeks. Their design is locked. The parts are being manufactured now. We're just waiting for everything to come in, pass quality control, do a little bit of final qualification, but it's a done deal. It just needs to be made now.
Very exciting. So what sort of price point are we looking at?
Under £100, and that's under £100 for a complete extrusion system. The hot end parts, the filament drive, and the motor. So you'll see a lot of extruders out there. The motor's an optional extra, and then you have to buy a hot end to put on it, and they still cost more than £100. This is £100 or less than £100 with the motor, with the the hot end and the filament drive advancing system.
Wonderful. So thank you very much for spending time talking to me today, Sanjay. Pleasure to meet you. Thank you very much. Thank you very much for watching. Don't forget to like and subscribe for more content from TCT 2019.